13.8 billion years ago, the universe was born in a state so ordered, so improbably smooth, that its very existence defies chance. Every second since, entropy has climbed, galaxies have scattered, and stars have burned towards silence. Yet the laws of physics, written at the smallest scales, make no distinction between forward and backward. They allow time to run both ways. Why then do we remember the past but never the future? Why does a shattered glass not reassemble, or the dead return to life? Is the arrow of time carved into the universe itself, or is it an illusion born of our own perception? From the birth of stars to the heat death of the cosmos, from quantum paradoxes to black hole horizons, the riddle deepens with every answer. Prepare for a journey where physics, philosophy, and mystery converge into the question that governs all others: why does time move forward? We begin. Time. It is the one companion we never chose, the one current no vessel can resist. From the instant of our first breath to the slow extinguishing of our final spark, it carries us forward without pause, without retreat. We do not command it, though we live entirely within its grasp. You feel it in the rhythm of your heart, in the aging of your body, in the way dawn slips quietly into dusk. We measure it with clocks and calendars, yet we have never truly defined what it is. We speak of hours and seconds as if they were tangible coins to be spent, but they are not objects. They are shadows of change, markers of transformation. Consider a candle burning in the night. Its flame wavers, its wax pools, and with each flicker something irreversible has happened. The wax does not climb back up the stem. The smoke does not fold itself back into the wick. Once the moment is gone, it cannot be summoned again. Time feels like that flame, a one-way fire consuming the future and leaving only ashes of the past. And yet, the strange truth is this: in the equations of physics there is no such command. Newton's laws, Maxwell's equations of electromagnetism, even the deep mathematics of quantum mechanics, all of them work perfectly well if you flip the film reel backward to nature's equations. The candle could burn in reverse, the wax reassembling, the smoke flowing back into the wick. Nothing in the mathematics forbids it, and yet in our lives, in our universe, we never see it. Why? This is the haunting paradox of time. The flow we cannot escape is not written directly into the laws of motion, but it is carved into our reality nonetheless. Somewhere between the austere neutrality of physics and the undeniable push of our experience, time acquires an arrow. It is this arrow we are chasing tonight. Close your eyes for a moment and imagine. A glass slips from your hand and shatters across the floor. The shards leap outward in all directions, scattering light. You can picture that clearly. Now reverse it in your mind, shards on the floor suddenly aligning, leaping together in perfect choreography, merging back into a flawless glass. The second vision feels impossible. Yet by the laws of physics, it is just as valid as the first. What prevents it? The answer lies not in the individual particles, but in the grand statistic of them all. There are infinitely more ways for disorder to increase than for it to decrease. Entropy, the name scientists give this spread of disorder, is the hidden hand behind the arrow of time. A million jumbled shards are vastly more probable than a fragile glass standing whole. Heat moving from hot coffee into cold air is inevitable, because there are so many microscopic ways for energy to disperse, and so few for it to concentrate again. This is the quiet tyranny of the second law of thermodynamics. In a closed system, entropy always increases, and with it, our sense of time flows forward. It is not the tick of clocks that gives time its direction, but the inexhaustible tendency of the universe toward disorder. But entropy alone does not satisfy the heart of the mystery. For why, we might ask, was the universe ever ordered enough to begin with? If entropy always grows, why was it once so low? How did the cosmos begin in such improbable symmetry, only to unravel across billions of years? We will travel deeper into that riddle soon. For now, we linger at the threshold, with the undeniable intuition that time is not just a coordinate but a current. Think of the ancients who first tried to measure it: the slow drip of water in a clepsydra, the sweep of shadows on a sundial, the grain of sand slipping in an hourglass. Each was a way to tame the river, to capture in a device what the body already knew, that change was steady, relentless, and irreversible. Civilizations rose around the rhythm of seasons, the cycle of harvest and flood, the waxing and waning of the moon. To tell time was not only to mark existence, but to anchor it. Yet even those earliest watchers must have sensed the paradox. A comet blazes across the night sky, retracing its path century after century. The stars wheel in patterns that seem eternal. To the heavens, time could feel circular, eternal return. To the human life, it was linear, carrying one from youth to age to dust. This duality, the eternal and the fleeting, still breathes within us. Modern science sharpened the paradox further. When Galileo dropped balls from the Leaning Tower, when Newton wrote of absolute time flowing equably, when Einstein later showed that flow itself is pliable, relative, bound to the fabric of space-time. At each turn, our understanding deepened but our certainty frayed. Time was not as simple as the hand of a clock sweeping its circle. And so here we stand, between two truths. In mathematics, the universe could run either way. In experience, it runs only forward. Let us imagine, for a moment, a world without time's arrow, a place where coffee warms itself, where smoke curls back into a candle, where broken glasses leap together whole. Such a place would not feel miraculous but horrifying, for it would betray the very logic of memory and cause. We know the past because entropy was lower. We do not know the future because entropy has not yet revealed its forms. In a sense, you could say memory itself is entropy's signature. To remember is to leave a trace. In neurons, in scratches on a rock, in photons traveling from a distant star. Each trace is a record of an increase in disorder. Without it, nothing would endure long enough to be known. And still, we are unsettled, because entropy explains the arrow, but not the origin of the arrow. It tells us why the river flows downhill, but not why the riverbed slopes in the first place. That question points us to the birth of the cosmos itself. Tonight, as we drift through this cinematic journey, we will walk that slope together, from the familiar experience of ticking clocks and falling glasses, through the deep mathematics of relativity and quantum mechanics, into the fiery birth of the universe and the silent possibility of its end. Time may be the one thing we can never outrun, but in seeking to understand its arrow, we glimpse the very blueprint of reality. Imagine standing in a silent room. In your hand is a cup of steaming coffee, rich and fragrant, alive with heat. Set it on the table, walk away, and in an hour the warmth has fled into the air. The cup grows cold, the steam vanishes. This is ordinary, unremarkable, and yet it is one of the deepest truths of the universe. The coffee never reheats itself. The steam does not return, condensing back into perfect swirls above the liquid. The flow is always one way. That flow, invisible but absolute, is what we call the arrow of time. It is an arrow hidden not in the ticking of clocks, but in the restless dispersal of energy and order. Scientists gave it a name: entropy. Entropy is not chaos in the casual sense. It is a measure of how many ways the pieces of a system can be arranged without changing its overall appearance. A shuffled deck of cards, a mixed bowl of sand and salt, molecules of air spread across a room. The more possible arrangements, the higher the entropy. And the second law of thermodynamics whispers with iron certainty in a closed system: entropy never decreases. This is why time has a direction. Consider again the glass falling from your hand. Before it shatters, there is only one way for it to exist: whole. After the shatter, there are billions of possible arrangements of fragments on the floor. Probability tilts overwhelmingly toward disorder. The glass does not leap back together, not because physics forbids it, but because the odds are so astronomically against it that in the lifetime of the universe, such a reversal will almost certainly never occur. Entropy gives us a statistical arrow. It does not command each atom. It does not forbid strange fluctuations, but as a vast tide, as the average of all possibilities, it ensures that tomorrow will always carry more disorder than today. This is the quiet dictator behind everything we know. Without entropy's increase, there would be no memory. For memory requires a record, the imprint of neurons altered, of ink darkened on a page, of photons frozen into a photograph. Each record is created by some increase in disorder, a transfer of energy, a scattering of particles. To know the past is to inherit its entropy. Without entropy's increase, there would be no aging. The cells of your body would not degrade, the strands of DNA would not accumulate errors, the tissues would not stiffen under the constant wear of microscopic collisions. Entropy seeps into our flesh, marks us with years, ensures that time's arrow pierces not just the universe but the body itself. Without entropy's increase, there would be no stars. Fusion inside a star burns because hot energy spills outward, balancing the collapse of gravity, spreading into the surrounding vacuum. Stars shine because entropy demands they must. They are candles lit by the universe's insistence that order dissolve into possibility. And so, when we say that entropy is the arrow of time, we mean that the universe's restless drive toward greater possibility is what gives our days their order. The arrow does not emerge from a clock's gears or from the rotation of Earth, but from the statistical tyranny of probability. Yet here lies a deeper mystery. If entropy always increases, then the past must have been more ordered than today, and yesterday more ordered still. Follow that regression far enough back and we confront an enigma. The beginning of everything must have been almost unimaginably ordered. And indeed, when we look at the earliest universe, when the cosmos was only a few 100,000 years old, we see this reflected in the frozen afterglow of the Big Bang, the cosmic microwave background. It is astonishingly smooth, nearly the same in every direction, with only the faintest ripples of imperfection. It was, compared to now, a state of breathtaking low entropy. But why? Why did the universe begin so improbably neat? If entropy is the deck being shuffled, why did the game begin with all the cards aligned? This is a question still unanswered. Some physicists suggest it was a matter of cosmic inflation, the rapid expansion of space, ironing out irregularities like a hot press on wrinkled cloth. Others argue that perhaps the laws themselves demanded such an initial state. And there are voices that wonder whether the question is even well posed, whether time itself may have emerged with that arrow already woven in. What we do know is that without this improbably low entropy beginning, the universe would have been stillborn. No stars would have formed, no planets, no galaxies, no life. Without the arrow, there would have been no future. And yet, if we zoom to the smallest scales, to the realm of particles and quantum fields, the paradox sharpens. At that level, the equations are time-symmetric. They do not favor forward over backward. A particle collision looks the same in reverse. Quantum laws permit both directions with equal ease. The arrow vanishes. It is only when we rise from the microscopic to the macroscopic, from the isolated particle to the trillion upon trillion interactions of matter and energy, that the arrow emerges like a ghost from the crowd. Entropy is not a law of individual things, but of enormous assemblies. It is the chorus, not the solo. This gives rise to strange possibilities. Theoretically, rare fluctuations could occur in which entropy decreases, a handful of air molecules, by sheer coincidence, clustering into one corner of the room. We never see it, because the probability is so absurdly low, but in an infinite universe, with infinite time, such fluctuations are not impossible. From this idea sprang a disturbing thought experiment, the Boltzmann brain. If entropy occasionally fluctuates downward, then it is statistically far more likely that a single brain, complete with false memories, could spontaneously form out of chaos than that an entire low-entropy universe like ours would exist. Are we such a fluctuation? Almost no one believes this is the real state of things, but the puzzle lingers, a shadow at the edge of probability. The arrow of time, then, is both deeply explanatory and deeply mysterious. It accounts for the ordinary, melting ice, cooling coffee, fading stars. It explains why we can remember yesterday but not tomorrow. But it also raises the profoundest questions. Why did the universe begin in such unlikely order? Could entropy ever truly reverse? Is time's arrow fundamental, or is it an illusion born of statistics? Even in human language, the arrow has shaped us. We speak of the past as behind, the future as ahead. We frame our lives as journeys with beginnings, middles, and ends. Our very grammar bends to the arrow, as if we cannot think without it. And so we return to the coffee on the table, gone cold. You could, in principle, calculate every molecular collision, trace the flow of every atom, and the equations would be indifferent to whether the film ran forward or back. But in practice, in life, in reality, there is only the forward spill of warmth into air. There is only the relentless climb of entropy. This is the hidden current that gives time its direction, the silent law that guarantees tomorrow will be unlike today. And it is only the beginning of the mystery, for beyond entropy lie deeper forces, relativity, black holes, the very birth and death of the cosmos. The arrow of entropy points us forward, but it does not tell us where the path ends. That journey continues. Imagine a great stage, vaster than any theatre, with no walls, no ceiling, no floor. On this stage, everything that has ever existed performs, stars pirouetting in arcs of fire, planets gliding in quiet ellipses, galaxies colliding in slow, magnificent spirals, and beneath them all, unseen yet absolute, lies the fabric that holds the play together, space-time. It was Albert Einstein who first taught us to see time, not as an isolated thread, but as one of the warp and weft of this fabric. For centuries before, Newton had spoken of time as absolute, flowing evenly, independent of events, like a cosmic metronome ticking above the universe. But Einstein, with the boldness of a poet and the precision of a mathematician, showed us something stranger. Time was not a detached observer. It was stitched inseparably to space itself. Picture this fabric stretched taut. A star presses down into it like a heavy ball on a rubber sheet. A planet rolls nearby and is drawn toward the star, not because of some invisible force pulling, but because the fabric itself curves, guiding the planet's path. This was Einstein's revelation. Gravity is geometry. The bending of space and time tells matter how to move, and the movement of matter tells space and time how to bend. But if time is part of that fabric, then it too must bend, stretch, and ripple. And here the mystery deepens. Imagine two friends standing side by side, each with a clock in hand. One climbs a mountain, while the other stays in the valley. Later, when they compare their clocks, they find that the mountain clock has ticked slightly faster. Time itself has flowed differently for them, simply because one stood higher in Earth's gravitational well. This is no thought experiment. We have tested it. Atomic clocks, with precision down to billionths of a second, have confirmed it. Place one on the floor and another on a shelf, and the higher clock will drift ever so slightly ahead. The difference is tiny, but real. Gravity bends not just space, but time. Now imagine an astronaut orbiting Earth in the International Space Station. She circles the globe at tremendous speed. Her twin brother remains on Earth. When they reunite, they discover that her clock reads a fraction of a second less than his. She has aged slightly less. For her, time has moved more slowly. Velocity too can dilate time. This is the famous twin paradox, a consequence not of science fiction but of Einstein's equations. Our technologies depend on these truths. The global positioning system, the web of satellites that guides airplanes, ships, and your phone, must constantly correct for relativistic effects. The satellites orbit higher, where Earth's gravity is weaker, so their clocks tick faster. But they also travel at great speed, which slows their clocks down. The balance of these effects is carefully calculated, or else GPS errors would grow by kilometers each day. Every navigation, every map, every guided missile and emergency call is a daily proof of Einstein's union of space and time. This is the strangeness of relativity. Time is not universal. It does not flow evenly everywhere. It is elastic, pliable, stretched by speed, distorted by gravity. The arrow of time may point forward everywhere, but its tempo, its rhythm, is not the same across the cosmos. Consider the edge of a black hole. As you fall toward its event horizon, your clock, strapped to your wrist, ticks as usual. To you, nothing is odd, but to a distant observer watching from safety, your time slows, then nearly freezes as you approach the horizon. From their perspective, you never quite cross. You simply fade into stillness, light stretched to red, until you vanish. Time itself becomes fractured, inconsistent, dependent on vantage. What does it mean, then, to speak of the present? If my now and your now can slip apart under gravity or velocity, is there any universal present at all? Einstein hinted that the answer is no, that past, present, and future are not absolute slices, but part of a single four-dimensional tapestry, each observer cutting through it differently, each line of now tilted by their motion and position. This is the seed of the block universe, the vision that all moments exist equally, already woven into the fabric, with time as a dimension no more privileged than length or height. To us bound in the current, the fabric feels like a river, but to mathematics, it is a frozen hole. And yet, relativity does not erase the arrow. The equations are symmetrical. The geometry could be traced backward or forward. The curvature does not explain why we cannot remember the future. For that, we must still turn to entropy. Relativity adds another layer. It shows us that the river flows at different speeds, that no two boats move in perfect sync. But it does not tell us why the river flows forward at all. There is poetry in this tension. At the human scale, time feels steady. Our clocks agree, our days march in rhythm. But climb higher, fly faster, dive deeper into gravity, and time itself fractures. Each perspective carries its own truth, yet all truths are bound together in the curved fabric of space-time. Sometimes, I imagine the universe as a vast loom. Space are the horizontal threads, time the vertical, matter and energy press, and stretch the weave, making valleys and peaks. We move along its strands, blind to the full pattern, sensing only the thread beneath our feet. Einstein, with rare genius, pulled back the veil and glimpsed the fabric entire. And even in his vision, mysteries remain. How fine is the weave? At scales smaller than the Planck length, does space-time remain smooth, or does it dissolve into quantum foam? Can this fabric tear in the heart of a black hole at the instant of the Big Bang? These questions bridge relativity and quantum mechanics, two great pillars of physics that have yet to be reconciled. Somewhere in their union lies the deeper nature of time. But for now, it is enough to stand in awe of what Einstein revealed, that time is not separate from space, but one with it. That gravity is not a force, but a curvature. That clocks can disagree not because they are faulty, but because the universe itself bends the tempo of existence. It is enough to remember that when you hold your phone and watch a blue dot crawl across a map, you are witnessing a triumph of this revelation. Each step of your journey is guided by satellites whose clocks whisper in the language of relativity, correcting for the warping of time above Earth's surface. You walk through Einstein's legacy every day. The stage of space-time stretches endlessly around us, curved by suns, rippled by planets, folded by black holes, and we, tiny actors upon it, are carried in its script, unable to step outside the weave. The arrow of time flows along its threads, stretched, slowed, but never reversed. From the geometry of space-time, we will soon turn again to clocks themselves, the devices we build to measure the unmeasurable, to catch in human hands what the universe bends at will. We live by clocks, the hands that sweep across a dial, the digits glowing softly on a nightstand, the chime of a bell in a distant tower, all are guardians of order, measuring the rhythm of our days. Yet beneath their steady tick lies a truth far less steady. Clocks do not always agree. At first this seems absurd. We build clocks precisely so that they will agree, so that 1 hour in Paris is 1 hour in New York, 1 second in orbit is 1 second on the ground. Synchronization is the lifeblood of civilization. Trains depart on schedule, stock markets open and close in unison, data flows through fiber cables at tightly controlled intervals. Surely time is the one constant we can rely on. But Einstein whispered otherwise, and our experiments have proved him right. The most precise instruments we have ever built are atomic clocks. They do not rely on gears or pendulums, but on the natural vibration of atoms. Inside their chambers, electrons leap between energy levels, releasing photons at frequencies so stable that the tick of such a clock is as steady as anything known in the universe. Today's best atomic clocks lose or gain less than a second over billions of years. To build one is to hold in human hands a fragment of eternity. And yet, place two atomic clocks in different conditions and their steady beats begin to slip out of sync. One famous test carried a pair of atomic clocks aboard commercial airplanes, flying them eastward and westward around the globe, while a third identical clock remained on the ground. When the journeys ended and the clocks were compared, they no longer matched. The differences were small, microseconds, but undeniable. The moving clocks had ticked differently than the one that stayed still. Velocity had bent the tempo of time. Another test lifted clocks up a tower, while others remained at the base. The higher clocks ticked faster. Gravity, too, had bent their rhythm. And in our modern world, satellites orbiting Earth carry clocks that must constantly be corrected for these very effects. If ignored, the difference would build until GPS signals failed, maps collapsed, navigation unraveled. Every time you check your location, you are trusting in relativity's correction, the silent proof that time is not universal, but local, pliable, relative. What does it mean then when two clocks disagree? Which one measures the true flow of time? The strange answer is both. Each clock is faithful to its own path through space-time. To the traveller on the plane, the seconds passed normally. To the twin who stayed home, his own seconds were just as real. There is no master clock above the cosmos, no single rhythm dictating all events. Time is a personal experience written into the geometry of one's journey. This truth unsettles the idea of simultaneity. Once it was assumed that now was the same everywhere, that the universe could be sliced into a single present moment stretching across the stars. But relativity dissolved that certainty. If two observers are in relative motion, what one considers now may be then or later to the other. The present itself fractures, tilts, bends. And yet, we do not feel this. To us, time seems absolute. Our clocks tick in unison. Our days are ordered. Our conversations make sense. That illusion is sustained because we live in conditions where differences are tiny, microseconds here, nanoseconds there. But scale it up to cosmic dimensions, to black holes and light-speed voyages, and the differences swell until simultaneity collapses. It is tempting to imagine time as a river, with every clock a boat drifting downstream. But relativity reveals that some boats drift faster, others slower, depending on their depth in gravity's well or their speed through space. There is no single current, only countless streams, all part of the same riverbed, but each flowing at its own pace. The oddity sharpens when we remember that these variations are not errors, but laws. The clocks do not malfunction. They reveal reality. If you lived your life aboard a spacecraft skimming the speed of light, your decades might be only a handful of years to those you left behind. Your clock would not be wrong. Theirs would not be wrong. Time itself would have fractured, stitched differently along your respective paths. This challenges the very notion of age. When astronauts return from long missions, they are technically younger than their Earthbound twins, though by fractions of a second. Still, it is a proof that age is not absolute. To ask, "How old am I?" is really to ask, how much time has passed along my path through space-time? And what of the cosmos itself? When we look deep into the night sky, we see galaxies billions of light-years away, their lights stretched across eons to reach us. We are looking into the past, into snapshots frozen long before Earth even formed. If time is relative, then what is happening now in those distant galaxies? The unsettling truth: there may be no universal answer. Their present and ours may not align in any absolute sense. Still, clocks remain our companions, imperfect mirrors of the infinite. They mark the beat of our lives, even if they refuse to march in universal step. And perhaps that refusal is a gift, a reminder that time is not a tyrant but a tapestry, a weave in which every observer's thread is valid, even when they do not align. Yet one mystery lingers. If clocks measure time differently, if simultaneity dissolves, how do we reconcile this with the arrow of time? Entropy still rises everywhere. Glasses still shatter in all frames. Coffee still cools. Stars still burn out. The direction is consistent even when the tempo is not. The arrow is universal, though the rhythm is not. This suggests a profound picture. The universe is not a single ticking clock, but a symphony of clocks, each instrument following its own tempo, each note stretched or compressed by motion and gravity. Together they form the music of space-time, dissonant yet coherent, fractured yet whole. Sometimes when I imagine the far future, I see explorers sailing among the stars, carrying their own clocks aboard ships that slice close to light speed. They will live years while centuries pass elsewhere. They will write letters home and receive answers only after their own grandchildren are dust. To them, time will feel natural, ordinary, yet their lives will diverge from Earth's rhythm irreversibly. The clocks will not agree, and that disagreement will not be an error, but a law of the cosmos. It is humbling. We once thought time was a single drumbeat echoing through existence. Now we know it is a web of tempos, elastic, relative, inseparable from space. And we, fragile and brief, are left to walk our own threads, each heartbeat one more tick in a local symphony. From here, our path bends deeper still into the quantum rebellion, where the very equations of matter refuse to acknowledge any arrow at all. If relativity showed us that clocks can disagree, quantum mechanics will ask whether time itself exists in the way we think it does. Step down now from the vastness of galaxies, from satellites and black holes, into the hidden chamber of the very small. Here, beneath the surface of atoms, the arrow of time begins to falter. The rhythm that felt so absolute in our lives, so undeniable in entropy's push, begins to blur, to dissolve into equations that care little for before or after. This is the strange rebellion of the quantum world, where relativity stretches and bends time but still acknowledges its flow. Quantum mechanics seems to regard time as irrelevant. The equations describing an electron's wave function, the probabilities of where it may be found, are perfectly happy to run forward or backward. Play the tape in reverse, and the mathematics does not flinch. There is no arrow here. And yet, when we observe the quantum world, when we dare to look, we find outcomes that seem irreversible. A radioactive atom decays, releasing energy into space. A photon strikes a detector, leaving behind a tiny flash. A quantum state collapses into a definite result. Each of these events appears to move in one direction, never to be undone. How can both be true? One answer lies in the peculiar way that quantum mechanics separates what can happen from what is observed. Until we measure, a system evolves smoothly, indifferently, its possibilities fanning out across time like ripples on a pond. But the instant we measure, those possibilities collapse into a single outcome. The atom has decayed. The photon has struck here, not there. The wave function has chosen. This collapse is what gives quantum events their apparent arrow. It is the moment the tape refuses to run backward, and yet the collapse is not part of the equations themselves. It is something extra, something mysterious, perhaps even an illusion of our own perception. Consider the famous paradox of Schrödinger's cat. Place a cat in a box with a vial of poison triggered by the decay of a single radioactive atom. Until we open the box, the atom is both decayed and not decayed. Therefore, the cat is both alive and dead. Only when we look does the cat collapse into one fate or the other. Time in the box is suspended, a quantum standoff between futures, until the act of observation tips the balance. But what is this observation? Must it be a human eye? A conscious mind? Or is any interaction with the environment enough? Many physicists argue that the universe itself, through a process called decoherence, continually measures quantum systems. Every collision of a photon, every interaction with stray atoms leaks information into the environment, collapsing superpositions into definite states. If so, the arrow of time in the quantum realm may emerge not from fundamental law, but from the unavoidable entanglement of systems with their surroundings. And here lies the heart of the rebellion. Quantum laws are reversible, but decoherence, like entropy, is not. Once the environment has absorbed information, it cannot be unabsorbed. Once the cat has interacted with the air molecules in the box, or the photons bouncing inside it, the delicate quantum state is lost forever. Irreversibility sneaks in through the back door, through complexity and entanglement, giving rise to the arrow we recognize. Still, the unease remains. If the underlying rules do not distinguish forward from backward, then is time's arrow merely a mirage of scale? At the deepest level, could the universe truly be timeless? There are interpretations of quantum mechanics that dare to say yes. The Wheeler-DeWitt equation, a candidate for describing the wave function of the universe itself, does not contain time at all. It is timeless, static, describing reality as a whole rather than as a sequence. In such a view, our sense of flow, of past to future, is an emergent illusion, born of entangled states and memory, not of fundamental law. This is difficult to accept. To us, time feels as real as breath. To suggest it is emergent, like temperature or pressure, is to strip away one of the pillars of existence. But science has always asked us to trade comfort for clarity. There are also interpretations that keep time but shift its role. In the many worlds picture, the wave function never collapses. Every possibility plays out, branching into new universes. The atom decays in one world, does not decay in another. The cat dies here, lives there. The arrow of time becomes the endless fracturing of worlds, each branch carrying its own unfolding future. In this vision, the direction of time is not dictated by entropy alone, but by the ever-growing multiplicity of realities. Others argue that quantum time is relational, that events do not happen at times, but that systems evolve relative to each other. One particle becomes a clock for another. There is no universal beat, only a web of correlations. Time, in this view, is not a backdrop but a relationship, something that emerges when systems interact. And yet, for all these interpretations, experiments remain agnostic. The mathematics works, the predictions come true, the technology flourishes. Quantum mechanics is the most successful theory we have ever built. Lasers, semiconductors, MRI machines, quantum computers, all are its children. But the meaning of its relationship with time remains an open wound, an unfinished symphony. It is here that the rebellion grows sharpest. Relativity and thermodynamics whisper to us that time is real, bent, irreversible. Quantum mechanics whispers that time is a ghost, an unnecessary label on equations that work just as well in reverse. Which is true? Perhaps both, perhaps neither. The clash between these visions is one of the greatest puzzles of modern physics. And still, in the quiet of the quantum realm, oddities bloom. Experiments have shown that particles entangled across vast distances seem to influence one another instantaneously, as if time does not matter at all. Photons measured here determine outcomes there, without any delay. Einstein called it spooky action at a distance, and though no information travels faster than light, the correlations defy ordinary time. Even stranger are delayed choice experiments, where particles seem to retroactively adjust their behavior based on measurements made after they should have already chosen. It is as though the future reaches back and alters the past, though most physicists explain this as a failure of classical intuition, not true backward causation. Still, the imagery unsettles. In quantum mechanics, the boundary between before and after is not always sharp. So what then is the quantum arrow of time? Does it exist at all? Or is it only entropy creeping in at the scale of trillions of particles that grants us the illusion of flow? Perhaps the answer is that time has layers. At the quantum level, it is symmetrical, indifferent. At the thermodynamic level, it gains an arrow through probability. At the relativistic level, it bends and warps with gravity and speed. Each layer adds a new rule, a new wrinkle in the fabric, and together they weave the time we experience. For us, the rebellion of the quantum world is not a threat but a reminder. That time, the river we swim in, is stranger than we can know. That beneath the flow of our lives lies a stillness, a symmetry, a possibility that the very distinction between past and future may not be fundamental at all. And if that is so, then our next step takes us even deeper into the paradoxes that bloom when quantum systems dare to flirt with cause and effect itself. When time's rebellion leads us into riddles no ordinary logic can solve. Open the lid of the quantum box, and you do not just find a cat. You find riddles clawing at the very fabric of causality itself. The rebellion of the quantum world does not end with time's symmetry. It deepens into paradox, a labyrinth of puzzles that tug at the threads of before and after. Imagine again Schrödinger's cat suspended between life and death until the box is opened. In one sense, this thought experiment was a parody, a satire of how absurd quantum mechanics can feel when applied to ordinary things. And yet, the paradox it exposes remains unsolved. What does it mean for reality to exist in superposition until it is observed? Is time itself paused in that box? Or is the cat's fate branching endlessly, in worlds we cannot see, long before we lift the lid? This puzzle is not confined to cats. It extends to every particle, every photon, every trembling electron in the universe. Consider the double-slit experiment, one of the strangest spectacles in all of science. Fire single photons at a screen with two slits, and they create an interference pattern, as though each photon passed through both slits at once, interfering with itself. But place a detector to see which slit the photon travels through, and the pattern vanishes. The photon chooses a path, observation collapses possibility into fact. But what counts as an observation? Is it a human eye, a machine, the environment itself? And if the interference pattern vanishes only when we measure, does this mean the act of measurement changes the past? That the photon was never both waves, but always a particle, hiding until we looked? Physicists have pushed this puzzle further with delayed choice experiments. In these, the decision to measure or not measure is made after the photon should have already traveled. Astonishingly, the results align as if the photon knew in advance, as though the future decision shaped the past behavior. Does the arrow of time bend here? Not in the ordinary sense. No information travels backward, no causality is violated, but the imagery is unsettling. Quantum experiments suggest that our tidy sequence of cause and effect is not so tidy after all. And then comes entanglement, the so-called spooky action that made Einstein uneasy. Two particles created together can be entangled, so that their states remain linked, no matter how far they drift apart. Measure one, and the other instantly reflects a correlated result, even across light years. Time and space seem powerless to intervene. It is tempting to imagine signals racing faster than light, slipping backward in time, but physicists assure us no usable information is exchanged. The paradox lies not in communication, but in correlation, in the way entangled particles behave as a single system across vast distances. Time does not separate them. Space does not divide them. They are one equation, stretched across the universe. Still, the feeling lingers. If the fate of one particle is determined instantly by the measurement of another, then what becomes of time's order? Does the universe know outcomes in advance? Or does entanglement reveal a hidden layer of reality, one that sidesteps our notions of sequence altogether? Some interpretations lean into this strangeness. In the transactional view, quantum interactions are not one-way messages but handshakes across time. Waves travel both forward and backward, meeting in the middle to form events. In this picture, the future and the past collaborate, writing reality together. It is a vision in which time itself is less an arrow than a loop of dialogue, a negotiation across directions. Speculative, yes, but such ideas remind us that quantum paradoxes are not just curiosities, they are cracks in our understanding of causality. And causality is what makes life intelligible. We drop a glass, it shatters. We strike a match, it ignites. We inhale, we exhale, without cause and effect. The world collapses into noise. But in the quantum box, causality trembles. Outcomes appear to depend not only on past conditions but on future choices. The line between before and after frays. Could it be then that our arrow of time is less fundamental than we imagine? That the flow we feel so deeply is not carved into the universe's core, but emerges only at scales large enough for entropy to dictate probabilities? In the hidden chambers of the very small, perhaps there is no flow at all, only a timeless dance of possibilities, collapsing into sequence only when touched by the macroscopic world. And if so, what does that mean for us, beings who live in the macroscopic? Are we too superpositions collapsing into choices as we move through life? Are our memories simply the branches we carry with us, while other branches, other futures, unfold unseen? Here the paradox becomes philosophical. If the arrow of time is emergent, then perhaps free will itself is tangled with it. If quantum outcomes are only probabilities until measured, then are our choices real decisions or collapses of cosmic dice? Some physicists recoil from this suggestion. Others embrace it as a possible bridge between physics and consciousness. In the end, the paradoxes in the box are not mistakes of science, but invitations. They beckon us to reconsider the meaning of time itself. They show us that our intuitions, forged in the scale of coffee cups and falling glasses, are ill-equipped for the theatre of the quantum. They remind us that reality is not obliged to make sense to human minds. And yet, there is a strange comfort in this dissonance. The box does not only confound us, it enriches us. It expands the horizon of wonder, showing that even in the smallest flicker of a photon lies a cosmos of mystery. From this chamber of paradox, we will soon step outward again to the largest scales, where the cosmos itself becomes the stage for time's arrow. We will rewind the universe to its earliest instance, to the moment when entropy was improbably low, when time's slope was first set. For if paradox rules the box, perhaps the answer to why time moves forward lies not in the smallest, but in the largest, in the birth of everything. Let us leave behind the box of paradoxes, the trembling wave functions and ghostly cats, and step outward, far outward, past the orbit of Earth, past the lantern glow of the stars, past the clusters of galaxies arranged like jeweled filaments in the dark. Let us rewind the film of the cosmos itself, rolling back eons, billions of years, until all this grandeur collapses into something smaller than a grain of sand. The arrow of time, so dominant in our lives, so persistent in entropy's rule, finds its ultimate origin here. For if entropy forever climbs, then it must have started low, and the lowest it has ever been was at the very birth of the universe. Roughly 13.8 billion years ago, space itself ignited in the event we call the Big Bang. This was not an explosion in the void, but the sudden expansion of the void itself. Energy and matter were born in the same instant, wrapped into a fabric of space-time that swelled faster than light. In those first fractions of a second, the cosmos was a furnace of unimaginable heat and density. And yet, despite the violence, it was astonishingly smooth. Imagine a vast plain, stretching in every direction, nearly flat, almost featureless. The density of matter and energy differed only by tiny fluctuations, 1 part in 100,000. This smoothness, this improbable order, is the puzzle that gives the arrow of time its slope. Why did the universe begin so improbably neat? Why not chaotic from the start? Some theories point to inflation, that strange brief era in which the universe expanded faster than even light could outrun. Inflation would have ironed out irregularities, smoothing wrinkles like a hot press on fabric. It explains the large-scale order we see today, the uniform glow of the cosmic microwave background. But even inflation begs the question, what set it in motion, and why was its initial state so finely tuned? Others suggest that the laws themselves demanded low entropy at the start, that the Big Bang was not just an event, but the inevitable beginning of order. Still, others wonder whether our universe is but one bubble among many, each born with its own arrow, some flowing forward, some backward. In that multiverse vision, our forward-moving time is a local property, not a universal decree. But speculation aside, what we can say is this. The universe began ordered enough to allow time's arrow to exist. Had it been born at maximum entropy, a uniform soup of energy and particles with no gradients, nothing could have happened. No stars could have formed, no planets, no life. It would have been a featureless eternal stasis, an existence without story. Instead, the low entropy dawn gave us structure. Gravity pulled matter into clumps. Stars ignited. Galaxies spun. Planets formed. Each of these processes was fueled by entropy's climb. Stars shine by scattering ordered nuclear energy outward into disordered radiation. Life grows by feeding on gradients, converting concentrated energy into diffuse heat. Civilizations rise on the same principle, burning fuel, scattering order into disorder. The arrow of time is the engine of everything. We see its imprint in the frozen light that still bathes the cosmos. The cosmic microwave background, this faint glow discovered accidentally by 2 engineers in 1965, is the aftershock of the Big Bang. A whisper of photons released when the universe cooled enough for atoms to form, about 380,000 years after the beginning. These photons, stretched into microwaves by the expansion of space, carry with them the memory of that ordered dawn. To look at the CMB is to see time's arrow etched into the sky. But rewind even further, to the first seconds, the first instants, and mystery thickens. At the Planck time, 10 circumflex 40, 4 seconds after the beginning, our physics collapses. Gravity and quantum mechanics, 2 pillars that otherwise describe reality so well, refuse to join hands. We cannot say with certainty what happened then. Did time itself emerge in that moment, or did something exist before the Big Bang, a concept that bends language itself, for before may have no meaning without time. Some theories whisper of a bounce, a universe collapsing from a prior cycle and rebounding into ours. Others propose that the Big Bang was a fluctuation in a greater timeless field, an awakening of space-time from nothing. Still others suggest that nothing is an illusion, that quantum laws churn even in apparent emptiness, spawning universes like foam on an infinite sea. What all these visions share is an acknowledgement. The arrow of time is rooted in beginnings we do not fully understand. Its slope was set at the start, but why it points forward remains unsolved. And yet, forward it points, from the birth of hydrogen to the forging of heavier elements and stars, from the clustering of galaxies to the emergence of life on a pale blue dot, the arrow has carried us. Every memory you hold is a product of that slope. Every word I speak is born on entropy's tide. But think of the strangeness in the grand equations. Time could run backward just as easily. A reversed Big Bang, a big crunch, is just as valid mathematically. Yet that is not our story. Our story is forward, unfolding, irreversible. Perhaps this is the greatest gift of the cosmic beginning. Not only that it set time in motion, but that it gave us story itself. For what is a story if not the flow of events from before to after, the unrolling of cause into consequence? A universe without an arrow would be a universe without narrative. And so, when we gaze into the deep sky and trace the redshift of galaxies, when we measure the faint uniform glow of the CMB, when we calculate the age of stars and the expansion of space, we are reading the diary of time's arrow. Every observation is a page written in the language of entropy, a testament that the universe began ordered and has been unraveling ever since. But this unraveling is not despair. It is the reason we exist. Without gradients, without the climb of entropy, there would be no chemistry, no biology, no thought. We are children of disorder, living creatures woven from the threads of time's asymmetry. The cosmic beginning is not merely history, it is present within us. Every atom in your body was forged in stars lit by entropy's demand. Every breath you take is a negotiation with time's flow. The arrow born in the Big Bang threads through your very cells. And as we drift further into this journey, we will see how this arrow stretches not only into the past but into the future, toward possible endings as mysterious as the beginning itself. But before that, we pause to look again at the frozen light of the cosmos, the great photograph of infancy, the proof that the universe remembers. Imagine a photograph so ancient that it predates stars, predates galaxies, predates even the formation of the first atom of carbon. A photograph older than Earth, older than the Sun, older than any memory life could ever hold. Such an image exists, though not in a frame on a wall or in an album on a shelf. It is written across the sky itself, stretched over the dome of the heavens, faint yet omnipresent, the cosmic microwave background. This frozen light is the oldest story we can read, a relic from when the universe was only 380,000 years old. An infant compared to its current age of 13.8 billion years. Before that time, the cosmos was too hot, too dense, too wild for light to roam freely. Photons collided constantly with electrons, trapped in a fog of plasma. Space was opaque, like the depths of a glowing furnace. But as the universe expanded, it cooled. Electrons joined with protons to form hydrogen atoms. At that moment, light was freed, the fog lifted. Photons streamed outward, finally released to travel unimpeded across space. Those same photons are still traveling. They have not stopped for nearly 14 billion years. Stretched by the expansion of the universe, their wavelengths have lengthened into microwaves. Invisible to our eyes, they bathe the cosmos in a faint glow detectable with the right instruments. To tune into them is to eavesdrop on creation. And what do we see when we map this frozen light? We see smoothness, a universe nearly the same temperature in every direction, with only tiny ripples, fluctuations in density so small, 1 part in 100,000, yet destined to become everything. Those faint blotches and speckles in the microwave background were the seeds of all galaxies, all stars, all worlds. In their whispers lay the blueprint of the cosmos. The discovery of this light was almost accidental. In 1965, 2 engineers at Bell Labs, Arno Penzias and Robert Wilson, were testing a radio antenna. They detected a persistent noise, a faint hiss, that would not go away no matter what they did, not from the instrument, not from Earth, not from the Milky Way. Eventually it dawned they were hearing the afterglow of the Big Bang itself. For this revelation, they were awarded the Nobel Prize, but more than that, humanity was given a time capsule of the universe's infancy. The cosmic microwave background is more than proof of the Big Bang. It is the clearest evidence we have that time's arrow began with an ordered, low-entropy state. Its near uniformity shows us that the early universe was improbably smooth, improbably simple, improbably poised to allow entropy to rise. Without this smoothness, the arrow could never have tilted forward as it did. And yet, in that uniform light, mystery lurks. Why was the early universe so even? According to entropy, randomness should dominate, but the CMB tells us otherwise. The cosmos was balanced on a knife's edge, smooth to a degree that defies naive probability. Inflationary theory explains part of this, suggesting that a burst of expansion ironed out irregularities. But even inflation requires conditions set with uncanny precision. The question remains, why? We also find odd asymmetries in the CMB itself. Though mostly uniform, certain large-scale patterns appear slightly lopsided, as if one half of the universe is subtly different from the other. Some scientists dismiss these as statistical flukes. Others wonder if they hint at something deeper, a hidden structure, a glimpse of a multiverse brushing against ours. What we know for certain is that these ripples, however slight, were essential. Without them, matter would never have clumped. No galaxies would have formed, no stars would have ignited. The universe would still be a smooth, sterile soup. In those tiny imperfections lay the seeds of all future complexity. Entropy's climb began there, in fluctuations that bent the arrow of time toward the richness of structure. Think of it. Every galaxy we see in the night sky, every cluster, every spiral, every brilliant quasar is the grown child of a faint blotch in that ancient light. Even the atoms in your body trace their ancestry to those fluctuations. In the grain of microwave static is the origin of you. We can map this frozen light today with astonishing precision. Satellites like COBE, WMAP, and Planck have scanned the sky, producing detailed portraits of the early cosmos. Their maps reveal not only the seeds of galaxies but also the geometry of the universe itself, showing that space-time is nearly flat, stretched wide by inflation. They allow us to measure the age of the cosmos, its composition of dark matter and dark energy, and the rate of its expansion. In the CMB, we read a cosmic ledger: 5% ordinary matter, 27% dark matter, 68% dark energy, the very balance of the universe, written in frozen photons. But beyond numbers, there is poetry in this ancient glow. Imagine those photons, born in a universe without stars, journeying across billions of years, slipping past, forming galaxies, dodging black holes, stretching across the dark to finally fall into our instruments. Each photon is a messenger, carrying with it a memory of the first time the universe could breathe. And in their persistence we see something profound light remembers. Even when matter collapses, even when entropy rises, photons preserve the trace of beginnings. In their survival, the universe keeps its diary. Yet this diary is also incomplete. The CMB shows us the universe at 380,000 years. But before that, in the first second, the first minute, the first heartbeat of existence, the pages are blank. We know little of those earliest moments. How matter and antimatter nearly annihilated, leaving just enough excess for stars to form. How the fundamental forces of nature separated from one another. How the seeds of inflation were sown. These questions remain veiled, the prologue missing from the photograph. Still, even the photograph we have is enough to stagger imagination. The arrow of time, tilted at the birth of the cosmos, is visible in its frozen light. Smoothness led to clumping, clumping to stars, stars to planets, planets to life. The story of becoming is written in microwave ink. Close your eyes and imagine the night sky, not as stars but as a soft, uniform glow, faint and ancient, stretching everywhere. That is the CMB. Sky without constellations, without galaxies, without history, only the quiet hum of a newborn universe. And yet, hidden in that quiet hum is the potential for all futures, the inevitability of entropy's climb, the assurance that time's arrow would carry forward. From this frozen light, we will now turn our gaze to the strangest distortions of the arrow, black holes, where time itself bends nearly to breaking. But remember, as we descend into those abysses, that the proof of time's direction is not only in shattering glasses or cooling coffee, it is etched across the heavens, in the faint hiss of static that whispers from the beginning. From the faint uniform glow of the infant universe, let us drift now into the darkest places it has birthed. The cosmic microwave background is the diary of beginnings, smooth and balanced. Black holes are the punctuation marks of endings, dense, violent, absolute. Where one showed us the arrow of time tilted by improbable order, the other shows us the arrow bent, warped, and slowed nearly to stillness. A black hole begins humbly. It is the corpse of a star, once brilliant, that burned through its fuel, gravity, no longer opposed by fusion's outward push, tightens its grip. The star collapses inward, its matter compressed past the point of ordinary atoms, past neutrons, into something so dense that even light cannot escape. What remains is a hole in space-time itself, a place where gravity is not a force but a geometry so steep that all paths lead inward. To speak of time near such a place is to enter strange territory. Imagine you are an explorer falling toward the event horizon, the boundary beyond which escape is impossible. To you, with a clock strapped to your wrist, time seems normal. Your seconds tick steadily, your heart beats steady. But to a distant observer watching your descent, something bizarre happens. Your time slows, your movements crawl. As you approach the horizon, you appear to freeze, suspended in space, your light stretched redder and redder until it fades into invisibility. From the outside, you never quite cross. From the inside, you fall freely. Both views are true, both are stitched into Einstein's geometry. Time itself has become relative not just in tempo but in meaning. This is gravitational time dilation in its most extreme form. We experience it weekly on Earth. Clocks tick faster on mountaintops than in valleys, but near a black hole, the effect grows profound. A few hours near its edge might equate to centuries far away. To linger there is to step into the role of a time traveler, not through machines of fiction, but through the geometry of space-time itself. Consider the thought experiment of a twin. One remains safely on Earth. The other ventures close to a black hole, skimming the horizon, then returns to the traveler. Perhaps a year has passed. To the twin left behind, decades, centuries or more may have unfolded. When they reunite, they are the same person split by the fabric of time itself. The black hole has become a one-way machine into the future. But the mysteries do not stop at the horizon. Deep within lies the singularity, a place where density is infinite and space-time curves without limit. Here our equations collapse. Relativity predicts a point of endless compression. Quantum mechanics recoils, demanding new physics. The singularity is the heart of the paradox, the place where time itself may end. And yet, black holes are not silent. Though light cannot escape, Stephen Hawking revealed that they are not entirely black. Through quantum effects at the horizon, particles flicker into existence, with one falling in and the other escaping. To a distant observer, the black hole glows faintly with this Hawking radiation, slowly losing mass. Over unimaginable spans of time, black holes evaporate. The titans of gravity fade into nothing. This raises a haunting question. What happens to the information they consume? If you fall into a black hole carrying a book, does the information in its pages vanish forever when the whole evaporates? If so, the fundamental laws of physics which demand that information is never destroyed are broken. This is the infamous information paradox, still unresolved. Some theories suggest that information is smeared across the horizon itself, preserved holographically in ways we cannot yet fathom. Others argue that it leaks back out through Hawking radiation in scrambled form. Still others imagine that black holes open tunnels to other universes, expelling information elsewhere. Each possibility challenges our understanding of time and causality. If information can vanish, the link between past and future unravels. Even stranger are solutions to Einstein's equations that hint at closed time-like curves inside rotating black holes, loops in space-time where one could, in theory, circle back and meet oneself. Could black holes harbor natural time machines, pathways into the past? Most physicists doubt such loops could survive the turbulence of reality, but the mathematics whispers of possibilities stranger than fiction. And black holes are not rare curiosities. They sit at the hearts of galaxies, millions to billions of times more massive than the Sun. They shape the cosmos, regulating star formation, sculpting galaxies with jets of radiation. Each is a monument to entropy's triumph, the final state of collapsed matter. They are the universe's most efficient engines of irreversibility. The arrow of time is carved deeply in their presence. Stars fall in, but never out. Matter spirals inward, never outward. Horizons grow, but never shrink, except in the slow whisper of Hawking radiation, itself a one-way climb toward disorder. In black holes we see entropy incarnate, the collapse of order into a geometry so extreme that time itself cannot escape. And yet, there is beauty here too. Black holes are not just destroyers, but paradoxical preservers. They hide within them the deepest puzzles of physics. They force us to ask whether time is fundamental or emergent, whether causality can survive the collapse of information, whether the universe itself is a kind of hologram projected from horizons. Imagine standing on a world orbiting near a black hole, watching its horizon like a great silent sun. Every second you spend there is a leap into someone else's future. You live in the slow river of time while galaxies whirl and age beyond you. To visit a black hole is to feel time's arrow not as invisible inevitability, but as a palpable weight, a presence bending around you. And in contemplating them, we glimpse how fragile our intuitions are. Time, which feels to us so steady, so absolute, is revealed as elastic, malleable, perhaps even breakable. Black holes are not merely cosmic curiosities, they are laboratories of reality, where the very notion of before and after is tested to breaking. From the frozen light of the cosmos to the frozen clocks at event horizons, the story of time carries us forward, deeper. Ahead lies an even stranger possibility, not just the warping of time, but the gateways it might permit. Wormholes, shortcuts through space-time, portals whispered by equations. If black holes are time machines into the future, wormholes tease us with loops that could reach into the past. And with them come the most haunting riddles of all paradoxes of cause, of choice, of existence itself. From the crushing darkness of black holes, let us turn toward their stranger cousins, doorways, not of collapse, but of passage. The equations of Einstein, when followed into their more exotic contours, reveal the possibility of bridges through space-time. We call them wormholes. They are the forbidden gateways, the shortcuts across the cosmos, the tantalizing promise of a path not just through space, but perhaps through time itself. Imagine the fabric of space-time as a sheet of paper. If you draw 2 points on that sheet, the shortest path is a straight line across the surface. But fold the paper, press the 2 points together, and suddenly the path between them is almost nothing. A wormhole is the fold, the tunnel, the bridge through dimensions. In theory, wormholes could connect distant regions of the same universe. In some solutions, they might even link different universes altogether. To step through such a gateway would be to walk from one cosmic shore to another without crossing the ocean in between. But more unsettling still, under certain conditions, a wormhole could serve as a time machine. Here's how. Suppose one mouth of a wormhole remains near Earth, while the other is carried on a high-speed journey, or held close to the edge of a black hole. Relativity tells us that time will pass differently at each mouth. When the mouths are brought back together, they are out of sync, connected not just across space but across time. Step into one, and you emerge not only elsewhere but elsewhen. It sounds like fantasy, and in practice it may be. For a wormhole to remain open, it requires a substance called exotic matter, material with negative energy density. No known form of matter behaves this way in large quantities. Without it, a wormhole pinches shut the instant it forms, snapping closed faster than light could traverse it. And yet, quantum physics teases us. In fleeting moments, the vacuum itself flickers with negative energies. Could these ghostly effects, magnified somehow, sustain a wormhole throat? Could advanced civilizations, wielding technologies beyond our comprehension, stretch space-time into a tunnel? The speculation lingers, suspended between impossibility and wonder. But even if such gateways exist, they come tangled with paradox. Imagine stepping through a wormhole to meet your younger self. You warn them not to board a plane, and so they do not. But if they never boarded, then you never suffered the events that compelled you to return. If you never returned, they never received the warning. The paradox coils back on itself, a snake devouring its tail. This is the grandfather paradox in cosmic clothing. What happens when causality loops? Physics stumbles here, for the very logic of time begins to tear. Some propose that paradoxes resolve themselves through consistency. The past cannot be changed, only fulfilled. In this view, If you travel back, every action you take becomes part of the history that was always there. You may try to prevent the event that sent you, but in doing so, you only ensure it happens. Time is a closed loop, immutable. Others invoke the many worlds interpretation. Each trip to the past births a new branch of reality. Kill your grandfather in one, and you erase your lineage there, but your original world persists untouched. In this view, wormholes are not paradoxes, but engines of divergence, spawning universes with every choice. Still others argue that nature itself forbids such violations. Hawking once proposed a chronology protection conjecture, suggesting that the laws of physics conspire to prevent closed time-like curves. Perhaps wormholes collapse the instant they are twisted into time machines. Perhaps quantum fluctuations tear them apart in a frenzy of radiation. Perhaps the universe simply says no. Yet we cannot dismiss the allure. To build a wormhole would be to step outside the tyranny of distance. The nearest star, 4 light-years away, would be a step through a doorway. The center of the galaxy, 25,000 light-years distant, might be a walk across a threshold. And if time's arrow could be bent along the way, we would hold in our hands the most forbidden of powers to unspool the order of cause and effect. Even if wormholes remain forever theoretical, they serve as mirrors for our imagination. They remind us that spacetime is not a rigid stage but a pliable fabric capable of folds and tunnels. They reveal how close our equations skate to the edge of paradox, how fragile the notion of a single timeline may be. In cinema and literature, wormholes often serve as portals of destiny, gateways through which heroes leap into futures unknown. But in physics they remain unresolved questions, shimmering at the horizon between what the equations allow and what reality permits. Perhaps the most haunting possibility is this: wormholes may exist, but we will never survive them. To approach their throats may be to encounter tidal forces that tear atoms apart. To step inside may be to dissolve into radiation. The gateways may be there, but forever forbidden. And yet, to contemplate them is to glimpse the audacity of physics. Einstein's equations do not only describe the orbits of planets and the bending of light, they permit tunnels through existence, loops in causality, cracks in the flow of time. Whether or not they exist in practice, they exist in principle, and that alone reshapes our understanding of what is possible. Close your eyes and imagine standing at the mouth of such a tunnel. On one side, the familiar stars. On the other, perhaps a galaxy millions of light-years away. Perhaps your own world centuries earlier. Perhaps a universe wholly alien, with laws unlike our own. You feel the pull of temptation to step through, to test the forbidden. But behind the temptation lies unease, for on the other side may not only be distance overcome, but causality undone. The arrow of time, so steadfast in entropy's rise, so pliable in relativity's grip, finds its most dangerous test here. Wormholes are the riddles of the arrow, places where forward and backward blur, where logic coils into paradox. They show us that the question, why does time move forward, is not just about physics but about the very coherence of reality. From here, our journey cannot help but dive deeper, toward the scale where relativity and quantum mechanics must finally collide, the Planck realm, where time itself may break into granules, and the weave of space-time may tremble into foam. Shrink your imagination now, down past atoms, past protons, past quarks, past the very fields that flicker beneath particles, into a domain so small that language falters. Here lies the Planck scale, the frontier of the unimaginably tiny, where distances are so short and times so brief that the known laws of physics no longer hold. The Planck length is about 1.6 Gots 10 circumflex 35 meters. To grasp its smallness, imagine stretching a proton across the observable universe. The Planck length would still be invisible, a whisper within that vastness. The Planck time is 5.3 9 Gots 10 circumflex 40, 4 seconds, the interval light takes to cross the Planck length. Beneath this scale, our equations collapse into uncertainty. Why does this matter for the arrow of time? Because at these depths, relativity and quantum mechanics, our twin pillars of physics, clash like rival kings over a fractured kingdom. Relativity describes the smooth curve of space-time, the bending of geometry under gravity. Quantum mechanics describes the jittering uncertainty of particles and fields. Each works brilliantly in its own domain, but at the Planck scale, both must be true at once, and in that collision, they break. What happens to time here? Some envision space-time dissolving into a foam, a froth of ever-shifting bubbles, wormholes flickering in and out of existence like quantum sparks. In such a froth, time may not flow smoothly but stutter, hiccup, fragment. Our sense of continuity might be an illusion, born of averaging over countless discontinuities too fine for us to perceive. Others propose that time is not fundamental at all but emergent, like temperature. Just as temperature arises from the motion of atoms, perhaps time arises from the interactions of quantum states. At the Planck scale, there may be no before or after, only a timeless landscape from which the illusion of flow emerges at larger scales. This is the domain of quantum gravity, the great uncharted territory of physics. String theory attempts to weave particles into vibrating strands, their harmonics giving rise to everything from electrons to quarks. In some versions, time itself is not a basic string, but a property that emerges from their symphony. Loop quantum gravity takes another route, suggesting space-time is not continuous but woven from discrete loops, tiny quanta of geometry. If so, time might tick not as a smooth river but as a granular beat, each Planck interval a pulse. And if time is granular, what does that mean for the arrow? Could entropy itself climb in jumps rather than a slope? Could causality blur between pulses, leaving gaps where before and after lose their meaning? These are not just wild speculations, but the questions serious physicists wrestle with in the silence of blackboards and simulations. One speculative idea is that at the Planck scale, the symmetry of time may be restored completely, that the arrow is a large-scale phenomenon, invisible at the fundamental level. If so, then our universe is like a painting. Up close, it dissolves into brushstrokes, chaotic and directionless. Only when we step back do we see the flowing image, the arrow of time stretching forward. But there are stranger visions still. Some cosmologists imagine the Planck epoch, the first 10 circumflex 43 seconds of the universe, as a place where time itself may have split. Our arrow pointing forward may be mirrored by another arrow pointing backward, into a universe that expanded in the opposite temporal direction. In this vision, the Big Bang is not the beginning of time, but the meeting point of two universes, each flowing away in its own arrow. To them, we are the backward ones. To us, they are. Both are true, and neither is privileged. If such a mirror universe exists, then entropy increases there too. But in what we call reverse, they would remember their past, never their future, just as we do. Their stars would shine, their galaxies would form, their civilizations might ponder why time moves forward, never knowing that their forward is our backward. Two arrows, born back to back, pointing into infinities unknown. This idea, though speculative, resolves the puzzle of why entropy was so low at the Big Bang, because the Bang was a place of symmetry, from which two arrows diverged. For us, the early universe looks ordered. For them, it does too. Both see the slope rising. Both are correct. And what of causality here? Could signals slip between arrows? Could particles born in one universe drift into the other? Some suggest dark matter might be such a residue, particles invisible to us because they belong to the other arrow, touching ours only gravitationally. It is speculation, yes, but speculation born of our ignorance at the Planck scale. The Planck frontier is not just a limit of size, but of knowledge. Our equations cannot see past it. To peer beyond requires a new theory, one that unites relativity and quantum mechanics. Until then, we stand at the edge of the smallest, staring into a fog as impenetrable as the black hole's horizon. And yet, this fog is not despair, it is promise. For every step humanity has taken in physics began with such limits. Once, atoms were the limit. Once, relativity itself was unimaginable. Now the Planck scale calls to us as the next frontier, the place where the nature of time may finally be revealed. Perhaps when the unifying theory is found, we will learn that time is not a line but a network, not a flow but a tapestry, not a dimension but a relation. Perhaps the arrow itself will be seen as an emergent trick, a way the mind organizes correlations rather than a fundamental feature. Or perhaps we will find that time is even more real than we thought, stitched into the quantum foam itself, indivisible, unavoidable. Whatever the answer, the Planck realm is the crucible in which it hides. Close your eyes and imagine the smallest flicker, a moment so brief it cannot be divided. a space so tiny it cannot be halved. That flicker, that space, is the Planck domain. Beyond it, our words collapse. Beyond it, the arrow of time may be reborn, reversed, or erased. From this abyss of the small, let us rise again, back into the scales we can see, to consider where the arrow of time might carry the universe as a whole. For just as it had a beginning, so too must it have destinies, and those destinies may be as strange and haunting as the Planck mystery itself. If the arrow of time began at the Big Bang, improbably ordered and tilting toward entropy's climb, then we must ask, where does it point? What is the fate of a universe forever moving forward? To trace the arrow backward is to find its mystery in beginnings. To trace it forward is to stare into the abyss of endings. The story of entropy does not end with cooling coffee or shattered glass. It stretches across billions of years, across galaxies, across the entire cosmos. The second law whispers not just about everyday decay, but about the ultimate trajectory of everything. To follow it is to glimpse the destinies of the arrow of time. One possibility is the heat death, the slow extinguishing of all gradients, all differences, all possibility. Entropy, climbing without pause, eventually reaches its maximum. Stars burn out, black holes evaporate, galaxies drift apart into silence. In the end, the universe becomes a thin mist of particles spread so evenly that nothing more can happen. No fire can burn, no star can shine, no memory can be written. Time, in a sense, loses its meaning, for without change, what is there to mark? This vision is chilling, an eternity of stillness, a cosmos not destroyed in fire but in quiet, a final dusk stretched across infinity. It is sometimes called the Big Freeze, the end not with a bang but with a sigh. But there are other visions, born of the dark energy that drives the universe's accelerated expansion. If dark energy remains constant, galaxies will continue to recede faster and faster, vanishing beyond horizons. Stars will form less often, the night sky will thin until distant light is lost. This too ends in a kind of isolation, civilizations forever cut off, islands in a darkening sea. If, however, dark energy grows stronger with time, its repulsion may not merely separate galaxies but tear apart galaxies themselves, then solar systems, then planets, then atoms. This is the Big Rip, a fate in which the arrow of time ends not in silence but in catastrophic disassembly. The very fabric of matter dissolves into nothing. Time ends not as a river fading, but as a torrent shredding itself apart. And yet, not all possibilities are so final. Some imagine that the universe might one day reverse its expansion, collapsing back inward into a big crunch. In such a scenario, time's arrow may tilt once more. Entropy would still rise during collapse, but as densities soar, as matter collides, could a new beginning be born? Might the big crunch ignite a new Big Bang, a cycle of death and rebirth, time flowing eternally through loops of expansion and collapse? There are stranger speculations still. Some propose that our universe is but one bubble in an infinite foam. As ours expands and fades, others are born, each with its own arrow of time, each with its own story. In this multiverse, time's destiny is not singular but plural. Our arrow is but one thread in an endless tapestry. But what does entropy say? In the heat death, entropy reaches its maximum, and the arrow loses its slope. In the Big Rip, entropy is carried to a violent extreme, scattering everything. In a cyclic universe, entropy may reset with each collapse, or perhaps carry forward, shaping each new cosmos with the memory of the last. None of these visions is certain. They are extrapolations, guesses carved from mathematics and observation. The truth is that we do not yet know the ultimate destiny of the arrow. Dark energy remains mysterious. The laws of quantum gravity remain unsolved. The universe may surprise us with endings beyond our imagination. And yet, these possibilities remind us of the fragility of time itself. We live in a brief window, a middle act. Stars still burn, galaxies still shine, entropy still has room to climb. It is in this fertile interval that complexity thrives, that life emerges, that civilizations wonder about their fate. The arrow of time, harsh as it may be, has granted us the stage on which to exist. Consider the irony. Without entropy, there could be no story. And yet, entropy is also the reason stories end. The arrow that makes memory possible also guarantees that one day memory will fade. The same law that allowed suns to form also ensures they will burn out. We live because time moves forward, and we will vanish because it does. Some thinkers see in this inevitability a kind of tragedy. Others see beauty, for is there not something sublime in being part of a story, even if it has an end? The universe itself is a narrative written in stars and galaxies, and like all stories, it is meaningful precisely because it flows from beginning to end. But perhaps endings are not endings. Perhaps they are transformations. In the heat, death, matter, and energy do not vanish. They spread, they dissolve, they become uniform. In the Big Rip, particles themselves may disassemble, but their energy still persists in some form. In the Big Crunch, death becomes rebirth, entropy feeding a new beginning. Even in silence, there is continuation. Even in stillness, there is presence. And if we are truly part of a multiverse, then perhaps our ending is only local, a chapter in an infinite library. Other arrows climb, other stories unfold, other beings ponder their fates. The arrow of time, so absolute within one cosmos, may be one melody in an eternal symphony. Yet even as we contemplate cosmic destinies, the arrow asserts itself here. Now, you feel it in your breath, in the slow pulse of your heart, in the way moments slip beyond grasp. We do not need the heat death to know time's finality. We feel it in the transience of each second. The universe's destiny is written in miniature within our own lives. Still, there is hope in knowledge. To trace the arrow is to understand the laws that govern us. To imagine the futures it allows is to glimpse beyond our brief lives, to find place within a story that spans billions of years. Perhaps we cannot escape entropy, but we can marvel at it. We can weave meaning within its current. Close your eyes and picture the final night sky. Galaxies have fled beyond sight. Stars have burned their last fuel. Black holes evaporate in faint whispers. The universe is quiet, and yet, in that silence, you recognize the culmination of a law that gave birth to everything you ever loved. Time has carried you here. The arrow, though it ends, was the very reason you existed to witness it. From these cosmic destinies, we must return to the present puzzle of philosophy. If the arrow points so unyieldingly forward, why do we sometimes imagine that all of time already exists? That past, present, and future are equally real? In this tension lies another vision of reality. The block universe, the frozen hole, the river disguised as flow. We have followed the arrow of time from the cooling of coffee to the collapse of stars, from the improbable smoothness of the Big Bang to the distant futures of silence or destruction. Again and again we find the same truth. Time flows forward. It is the one current we cannot resist, the background rhythm to every breath and every memory. And yet physics dares to whisper another vision, a vision that unsettles as much as it illuminates. What if time does not flow at all? What if the arrow is not a river carrying us forward, but an illusion born of perspective? What if every moment, past, present, and future, exists already, side by side, woven into a single eternal fabric? This is the block universe. In the block view, space-time is a four-dimensional whole. Every event that has ever happened, every event that will ever happen, is inscribed within it. The birth of a star, the fall of an empire, the flicker of your next thought, all are coordinates, etched forever in the block. There is no universal now, no privileged slice of time sweeping across the cosmos. The flow of time, the passage from past to future, is not a property of reality, but of consciousness. It is a disorienting thought. To us, time feels as real as touch or taste. We sense its movement in every heartbeat, in the way memories trail behind us and possibilities lie ahead. But relativity shakes this certainty. If simultaneity is relative, if what is now for you is then, for someone else moving differently, then how can the present be universal? The block view resolves the puzzle by discarding the flow. There is no moving present. The universe simply is. Imagine the block as a grand sculpture, carved in 4 dimensions. You are not moving through it. You are part of it. Every step you have taken, every word you will say, every future you will live, all are already inscribed. To you, it feels like a journey, but from the outside it is a landscape, still and complete. And here, the arrow of time finds its strangest interpretation. In the block universe, the arrow is not the flow of time itself, but the ordering of slices within the block. Entropy increases from one slice to the next, giving us the impression of movement, but nothing is truly moving. The increase of disorder is not progress through time, but structure within the block. Does this mean the future already exists? That your choices are already written, as fixed as the past? This is the deep philosophical weight of the block view. It seems to deny free will, to flatten possibility into inevitability. Every decision you imagine making tomorrow is already carved into the block. Every path you could have taken but did not exists nowhere. And yet, our experience resists this fatalism. We feel ourselves choosing. We feel the openness of the future. Could it be that free will itself is an emergent property, a way consciousness experiences the block from the inside? From outside, the path is fixed. From inside, it feels alive, unfolding. Both perspectives might be true depending on vantage. Some philosophers and physicists accept this fully. We are passengers in a frozen universe, living the illusion of flow because our minds experience slices sequentially. Others rebel, insisting that the flow must be real, that the block cannot capture the essence of becoming. The debate remains unresolved, one of the great open questions at the boundary of physics and philosophy. Still, the block universe has its elegance. It harmonizes with relativity, explaining why now is relative without contradiction. It explains why physics is time-symmetric at the fundamental level, because all times exist equally, none privileged. It even resonates with certain interpretations of quantum mechanics, in which probabilities describe not the unfolding of futures, but the distribution of outcomes already inscribed. But if the block is real, why do we feel time's passage so vividly? Why do we remember the past but not the future? One answer lies again in entropy. Memory is physical, written in traces, imprints, neural changes. Those traces exist in one direction, from lower entropy to higher. We remember the past because it left records. The future leaves none. Thus we experience flow. Thus the arrow feels real. Another answer may lie in consciousness itself. Perhaps the brain constructs the sense of now as a survival tool, stitching sensory input into a coherent sequence. The illusion of passage may be no different than the illusion of color, a construct of the mind, useful but not fundamental. And yet, illusions are powerful. The block may be frozen, but within it, we are alive. We experience joy, sorrow, choice, and meaning as though the river flows. If the block is real, then we are creatures designed to navigate it, not as gods outside of time, but as beings immersed in it. The arrow, whether fundamental or emergent, remains our lived truth. There is also a strange comfort here. If every moment exists already in the block, then nothing is ever lost. Your childhood, your first love, the laughter of friends long gone, all remain etched into the fabric forever. To us, they are past. To the block, they are simply coordinates, eternally there, eternally real. The future too already exists in this view, though we cannot see it, though it feels uncertain, though it arrives like surprise, it is as fixed as the past. Every star yet to be born, every civilization yet to rise, every breath yet to be taken is already inscribed. The arrow is our perspective, not reality's law. Of course, not all physicists agree. Many argue that the block view is incomplete, that it strips away the essence of becoming. They believe time's flow is fundamental, that the universe truly evolves, that the future is not yet real. The debate continues, unresolved, at the cutting edge of philosophy and physics. Perhaps the truth is subtler still. Perhaps the block is real, but so is the flow in different senses. From outside, the block is fixed. From inside, the flow is lived. To deny either is to deny half the experience. Close your eyes and picture the universe, not as a movie, but as the real itself. Every frame present, every moment inscribed. That is the block. Now imagine yourself watching, frame by frame, carried along, unable to skip ahead. That is the arrow. The film is already complete, but the watching makes it real. From this contemplation of the block and the river, we must turn inward, to the minds that perceive the flow, to the consciousness that stitches experience into memory, to the fragile vessels in which time becomes personal. For whatever the cosmos decrees, it is in the human mind that time is truly lived. If the universe is a block, fixed and eternal, then why does it feel to us as if time flows? Why do we sense its passage as keenly as we sense light on our skin or sound in our ears? Perhaps the deepest mystery of time is not out among galaxies or at the Planck scale, but here, inside the human mind. For time, as we live it, is inseparable from memory. Without memory, there would be no past, no sense of before. Without anticipation, no future, no sense of after. Our perception of time is a stitching together of moments, a narrative written by neurons. Imagine waking in a world with no memory. Each instant would stand alone, unconnected to the last. There would be no arrow, no flow, just a perpetual now flashing and vanishing. The mind, in its fragile biology, is what binds the block into a story, what turns entropy's slope into lived experience. Neuroscience tells us that memory is physical. Each recollection is etched in synaptic changes, in patterns of firing across networks of cells. Memories are not films stored whole but reconstructions, reassembled anew each time we recall them. They are traces, imprints, physical scars of past events, and just like fossils in stone, they point in only one direction. We remember the past because it leaves records in our minds. The future has left none. This is why the arrow feels real. Entropy increases, leaving traces behind. The broken cup, the cooling coffee, the faded photograph, all are records of what has been. None are records of what will be. Our minds mirror this asymmetry. We remember backwards, never forwards. And yet, there are glimpses where perception blurs. In dreams, time distorts, seconds stretch into hours, events unfold without continuity. In trauma, time can slow, each detail etched with unbearable clarity. In flow states, it can vanish altogether, hours passing unnoticed. The brain is not a perfect chronometer. It is an artist, sculpting experience. Philosophers call this the psychological arrow of time. It may not be fundamental, but it is decisive for us. For whether or not the block exists, whether or not time truly flows, we live by memory, by anticipation, by the fragile thread that links moments into a story. Without it, there would be no self. Think of the patient HM, whose hippocampi were removed in surgery. He could no longer form new memories. Each moment was present, vivid, but disconnected. He was trapped in a perpetual now, unable to move forward in the narrative sense. To watch him was to witness what it might mean to live without time. And so we see that consciousness is not merely an observer of time, but a participant in its construction. The arrow of time for us is not only physics, but psychology. It is shaped by entropy, yes, but also by neurons, by perception, by the peculiar architecture of the brain. Speculative ideas go further. Some suggest consciousness itself may create the flow of time, that without minds to perceive it, the block would remain static, frozen, meaningless. In this view, time is not an objective feature, but a relation between universe and observer. Just as sound requires an ear, time requires a mind. Others resist this. Time, they argue, would exist whether or not we were here to perceive it. Galaxies would still spin, stars would still burn, entropy would still climb. Yet even here, there is mystery. For physics describes change but not experience. It tells us how matter evolves, but not why that evolution feels like flow. Memory also introduces the puzzle of free will. If the block is real and the future is fixed, then our choices are already inscribed. But to us, they feel open, undecided, contingent. Perhaps the sensation of making choices is a byproduct of memory. We recall the branching of the past and project that branching onto the future, even if only one branch will be real. Still, this illusion, if illusion it is, carries weight. For we act as though choices matter, and within the lived arrow, they do. Meaning arises in the gap between memory and anticipation, in the feeling of being carried forward through time's current. Whether or not it is fundamental, it is profound. The psychological arrow also reveals strange asymmetries. We remember the past with detail, but the future with vagueness. yet physics treats both directions equally in its equations. Could it be that our asymmetric memories are what give rise to the impression of an asymmetric universe? That our minds are not merely reflecting the arrow of time but co-creating it? Speculation reaches further. Some neuroscientists wonder if consciousness is linked not just to the present but to the construction of temporal windows. When you hear a melody, you do not perceive each note in isolation, you perceive them as a sequence stretched across seconds. Consciousness, then, is not a point but a span, a moving window stitching events into coherence. Without that stitching, the arrow would unravel. In mystical traditions, the present moment is often exalted as timeless, beyond the arrow. Meditation, deep stillness, trance. In these states, practitioners report the dissolution of past and future, the immersion into a now that feels infinite. Perhaps this too is a clue that time as we know it is not ultimate but constructed, and that the mind can in rare states slip its grip. And yet, even in these states the arrow returns, memory flows back in, the present becomes past, the body ages, entropy climbs, the mind may transcend briefly, but the universe continues its march. The psychological arrow is bound to the physical one, as surely as a leaf is bound to the river. There remains a haunting question: if consciousness helps shape the flow of time, could it also one day perceive it differently? Could advanced minds, artificial or biological, experience time not as a line but as a landscape? Could memory and anticipation blend into a perception of the block itself, the whole sculpture at once? To such beings, the arrow might dissolve. They would not remember the past or anticipate the future. They would see all moments equally, an eternal now stretched across eternity. For us, though, the arrow remains. It is in our blood, in our neurons, in the fragile thread of memory. We live by it, we love by it, we lose by it. Without it, we would not be. Close your eyes and feel the beat of your heart. Each thump is a record, a trace, a memory written into the body. Each breath is a measure of time, a step along the arrow. Your mind, sculpting experience, turns these beats into a story. The story feels like flow. The story feels like life. And so we see that the arrow of time is not only out there in the cosmos, but in here within us. It is both physical law and lived sensation, both entropy and memory, both universal and personal. From the fragile theatre of the mind, let us turn once more outward to the laboratories and instruments with which humanity has sought to test the arrow itself. For if time is mystery, then it is a mystery we have dared to measure, to probe, to experiment with at the edges of what is known. The arrow of time may feel inevitable, carved into the marrow of existence, but for centuries we have refused to accept feeling as proof. Humanity has built machines to measure it, theories to test it, instruments to stretch its meaning. If time is mystery, then we have met that mystery with experiment, and what we have found both confirms and unsettles the flow we take for granted. Begin with the simplest clock, a pendulum, swinging back and forth. Its tick and tock seem eternal, but friction steals energy, air resists the swing, entropy rises, and the pendulum slows. Here, in this common device, the arrow declares itself, order collapsing into disorder, reversibility yielding to decay. But pendulums are crude. To probe time more finely, we needed better tools. The most precise of all are atomic clocks. They do not count swings or cycles, but vibrations of atoms themselves. A cesium atom, for example, ticks 9,192,631,770 times per second. Each vibration is a measure, each tick a slice of time. These clocks are so accurate they would lose less than a second in the age of the universe. And with them, we discovered that time does not flow the same everywhere. Place one atomic clock on the ground and another in a plane flying high above. When reunited, the airborne clock has ticked faster. Gravity slows time. Place one clock in orbit, another on Earth, and they drift apart. Motion slows time. The universe does not give us one river of time, but countless, each flowing at its own rate, shaped by velocity and gravity. This is no thought experiment. It is practical fact. Without correcting for time dilation, the GPS satellites guiding your phone would be off by kilometers within a day. Every map, every navigation, every digital step is possible only because we know time does not flow evenly. The arrow is not only forward but pliable. bending with the geometry of space-time. Other experiments probe deeper still. In particle accelerators, physicists hurl protons together at near-light speeds, smashing them into showers of fragments. Among the debris are unstable particles that live fleeting lives before decaying. What they reveal is subtle. In some cases, the laws of physics treat matter and antimatter differently. This tiny asymmetry, called CP violation, may explain why our universe contains something instead of nothing. It is a clue that the arrow of time is written into the very fabric of particles. But quantum mechanics complicates the picture. At its heart, the equations are time-symmetric. They work as well backward as forward. To test this, physicists create entangled particles, twins linked beyond space. Measure one, and the other responds instantly, no matter how far apart. To us, it feels like the future depends on the present. But in quantum theory, it is as though time itself has no preference. Cause and effect blur. Some experiments even hint at retrocausality, where present choices appear to influence past states. In delayed choice experiments, particles seem to decide how they traveled only after we measure them. Did the future reshape the past, or is our sense of sequence an illusion? These puzzles force us to ask whether time's arrow is absolute, or whether at quantum scales it dissolves. At larger scales, scientists listen for ripples in space-time itself. Gravitational wave detectors like LIGO stretch arms 4 kilometers long, lasers bouncing with exquisite precision. When two black holes collide a billion light-years away, they send a shudder through space-time that vibrates those mirrors by less than a fraction of a proton's width. To detect such tremors is to feel time itself quiver, distorted by events across the cosmos. Here again, the arrow asserts itself. The waves carry history. The final moments of orbit, the plunge into merger, the settling into silence. They arrive stretched by cosmic expansion, their frequencies climbing downward, entropy rising, even in the song of space-time. Still, questions remain. Could we ever build an experiment that directly tests time's flow itself, not just its effects? Could we detect if the arrow were to reverse? Some physicists propose experiments in nuclear physics that could reveal tiny violations of time symmetry, evidence that the arrow is more fundamental than the equations suggest. Others dream of tabletop tests for quantum gravity, where the granularity of time at the Planck scale might flicker into view. And what of time travel? Experiments cannot build wormholes or closed loops, but they can search for their signatures. Physicists have scoured cosmic rays for evidence of tachyons, hypothetical particles that always move faster than light and might break causality. None have been found. Others search the sky for repeating patterns that might betray signals sent backward through time. So far, silence. The arrow holds firm. Yet experiments do reveal the malleability of time as we live it. Neuroscientists track the brain as it perceives seconds, as it stretches or compresses them in emotion, as it distorts them in dream. Psychologists measure the way boredom slows time, how joy accelerates it, how trauma freezes it. In the lab, they see what we feel. The arrow is as much a construction of mind as of physics. Perhaps the most haunting experiment is not yet built. Some imagine a quantum computer vast enough to simulate entire systems, to predict outcomes not step by step, but all at once. To such a machine, time as we know it might dissolve. It would not need to run forward. It could solve in parallel. Would such a computer reveal that time's flow is nothing but a computational trick, a byproduct of limited processing power? For now, we work with the tools we have: atomic clocks, accelerators, detectors, telescopes. Each reveals a piece of the puzzle. Together, they tell us that time is not absolute, not universal, not simple. It is local, pliable, tangled with entropy, bound to memory, slippery at the quantum edge. And yet, through every experiment, one truth persists. We cannot make it flow backward. The arrow remains unbroken. Every clock ticks forward. Every particle decays into disorder. Every memory looks behind, not ahead. Experiments at the edge confirm what experience already whispers. Time moves forward, never back. Close your eyes and imagine standing in a laboratory, lasers humming, detectors waiting, screens glowing with data. You feel not just the hum of machines, but the pulse of the universe itself, measured and tested. Humanity, fragile and small, has built instruments to question the current that carries all things. And though the answers are not final, though mysteries remain, the very act of measurement is a triumph. For in probing time, we glimpse not only the cosmos but ourselves, our need to know, to measure, to understand. From these laboratories we must travel one last step, beyond instruments, beyond theories, into the silence where time itself may end. For if the arrow began, and if it must end, what lies beyond both? We have journeyed across the vast terrain of time, from the everyday ticking of clocks to the birth of the cosmos, from black holes that slow time nearly to stillness to the quantum froth where time may not exist at all. We have followed the arrow through entropy, through relativity, through memory, through paradox. And now, at the end of this path, the question remains, what if there is a silence beyond time? Imagine the arrow coming to rest. No more stars are born, no more galaxies collide, no more atoms decay. In the great heat death, time does not end in an explosion or collapse, but in stillness, without change, without difference, without entropy left to climb. Time loses its markers. Seconds, minutes, years, they no longer matter. All becomes one eternal pause. Or picture the Big Rip, where expansion accelerates until galaxies, stars, planets, even atoms are torn apart. Here, time ends not in stillness, but in rupture, in the dissolution of all structures. Yet even in this final disassembly, the arrow fulfills itself, entropy rising, order dissolving, history scattering into nothingness. There is also the possibility of cycles, universes collapsing and rebirthing, time looping in infinite arcs. In such visions, silence is never final. Instead, it is a pause before rebirth, a breath before another act in an eternal play. Time, in these cycles, is not a line but a wheel, spinning without end. And yet, perhaps the silence beyond time is not cosmic but personal. For each of us, the arrow ends not in billions of years, but in the fragile span of a single life. Our stars burn briefly. Our memories gather entropy, fade, dissolve. For us, time's silence is not abstract but intimate. Death is the personal heat death, the local end of becoming. And still we face it with wonder, for to have lived at all is to have moved along the arrow. Some traditions suggest that beyond this silence lies eternity, a realm where time no longer applies. Eternity is not infinite duration, but absence of duration, a state beyond before and after. Physics cannot speak here, but poetry can. Close your eyes, and you may feel it, that stillness beyond the ticking of clocks, the eternal now whispered in meditation, in dream, in breath. Perhaps that silence is already within us. When you fall asleep, when dreams dissolve, when consciousness rests, time vanishes. Hours pass in the blink of an eye. For you, they never happened. Sleep is a rehearsal for that greater silence, a reminder that time's hold is not absolute. The silence beyond time may not be frightening but peaceful. Without clocks, without deadlines, without entropy, there is only rest. A universe at peace, a mind at rest. Time as river ceases, but existence, in some form, persists, whether in particles, in energy, in memory etched into the block of space-time. This final thought may bring comfort. If the block universe is true, then no moment is ever truly lost. Your laughter, your breath, your joy, your sorrow, all remain inscribed forever. The silence beyond time does not erase them. It simply means no new pages are written. The book remains, eternal, already whole. And if the block is not real, if time is truly flowing, then its end is still not nothing. For what has been remains. The arrow carried you here. The arrow gave you being. To reach its end is not defeat, but completion. Humanity, fragile and brief, has looked at the stars and dared to ask why time moves forward. We may never answer fully. Perhaps the arrow is born of entropy, or memory, or something deeper still. But in asking, in wondering, we have turned the arrow into meaning. We have written stories. We have created beauty. We have loved. The silence beyond time, then, is not something to fear. It is the final rest after the great movement, the last chord after the symphony. Time's current carried us, and then it lays us gently down. Now as our journey closes, let the imagery slow. No more rushing arrows, no more collapsing stars. Instead, feel the quiet. Hear your breath, steady and calm. Sense your body here in the present, grounded on Earth, far from galaxies and black holes. The mysteries remain, but they can rest. You can rest. The arrow of time flows, but for now you need not chase it. You need only drift, gently, into stillness. And so our journey ends, not with answers, but with questions softened into silence. We have walked the long arc of time, from the smallest quanta to the fate of the cosmos, and still the arrow flows. Yet in the quiet after such a journey, there is space to breathe, to let the immensity of existence dissolve into something tender and close. Time surrounds us, yes, but in this moment you can let go of its current. The past is memory, the future is possibility, but here, now, there is only presence. You are safe in this stillness. The stars can wait, the equations can sleep, the arrow flows on without your effort. In the vast block of space-time, your life is inscribed. Every smile, every sorrow, every fleeting second. Nothing is lost. Everything that has been is forever part of the universe's story, and in that story, you are enough. So close your eyes, feel the weight of your body sink deeper into rest. Let the arrow carry you gently, not into questions but into calm. Beyond entropy, beyond stars, beyond memory itself, there is a silence waiting, not emptiness but peace. The universe holds you timeless and vast. In its stillness, may you find sleep, may you find comfort, may you find dreams.